Hi everybody, welcome to our next lecture on computer animation. Today about parametric curves. So let's start with the properties. Remember that we obtain a parametric curve, which we call Q of u, with the helper variable u. Oh, so this should be variable, typo. And we have control points pi. So pi are vectors in 3D which contain the three coordinates x, y, and z. So we have several points and we call those control points. And then this parametric curve basically interpolates between those points using this formula here. We can see it uses those control points pi, and then it has a weighted sum. And the weights of this sum are determined by the polynomials bi. Right? So for each point we have a polynomial, an associated polynomial here, which depends on this helper variable u. And this polynomial is between 0 and 1, and it adds up, all those add up to 1, as you can see here. Because then we get a so-called convex hull. So if the sum of the basis functions bi of u over the unit interval of u between 0 and 1 is equal to 1, like expressed in this equation here, right? So they add up to 1 for all u's. So every u, every value of u in this interval always leads to the sum being 1. And if they are non-negative, then each point on the parametric curve is a weighted average of its control points. Right, so that's basically a definition of a weighted average. We have those points, we give them weights between 0 and 1, and if they add up to 1, then all points are located in the convex hull of the control points. Right, so that can be seen here. So here we have the control points, the PIs, in 3D space. And then we make this convex hull, this pyramid shape here, which you can see. And then we have this curve, which is a line because this u is one-dimensional, right? So basically we interpolate those three control points. We will get a point inside this pyramid. And where inside depends on those functions bi, right? So if we vary u between 0 and 1, we might get this curve, right? It looks like this. And this convex hull here that we can span is practical, for instance, for collision detection when we have, for instance, a video game. Yeah, so useful functions that those polynomials bi must fulfill are, for instance, this so-called affine invariance. So let's say phi is an affine transform, for instance, rotation or stretching. Then the basis function is affine invariant if the following applies. So we basically apply this rotation or stretching to this curve, right? And that's the same as applying this rotation or stretching to the control points alone, and then do a new interpolation between the transformed control points. Right? And that's an advantage because then we just need to apply this stretching or rotation to the control points, and the rest is done automatically. Right? We don't need to apply this transform to all the resulting points of the curve. So that's beneficial. Yeah, so basically the transform of the points of the curve can be replaced by a transform of the control points. So that's reduced calculation effort for scaling, rotation, position change, or similar. In computer graphics, we usually have affine invariant basis functions. So here those BIs are affine invariant. So here are some examples, or the mathematical formulation. So this would be for cubic curves. So here we have a mathematical formulation for cubic curves, which means we have polynomials of third order, which you can see here. We have the maximum exponent is 3, right? So then we get these three coordinates, x, y, and z of u, and each depends on this helper variable, and this is formulated as this third order polynomial. So we have coefficients a, b, c, and d for each of those coordinates. Right. So basically, we express our curve q of u as those three coordinates depending on u. So observe, we don't have any control points in it yet. Right. This is just the most generic or general formulation. So since we have polynomials of third order, we can basically simplify this very generic formulation as a multiplication of a vector containing the exponents of our helper variable u. See, this is u to the power of 0, u to the power of 1, then 2 and 3. So here we have this vector. And then we collect all those coefficients of those polynomials into this matrix. Right, and you can see if you multiply this vector by this matrix, you have this row vector times the first column vector here results in this first polynomial, the x polynomial. Then we multiply this row by the second column, and the result would be the y polynomial. And finally, the z polynomial. Right, so this is exactly what we see here. So in this way, we simplified the formulation from polynomial to a vector of exponents of u times a matrix. And this is also called a basis matrix. Yeah, so this is fairly generic, and we still don't quite know how to choose those coefficients of the polynomials. So it would be more practical to have a more geometric interpretation or design, right, instead of finding out the coefficients ourselves. So for easier handling, the coefficient matrix is divided into a base matrix and a geometry vector, right? So here we have our base matrix, and here we have some geometry vector, and this contains now vectors. We don't say what the meaning of those vectors is yet, right? It's just a connection to the geometry. So here we have 4 vectors, and each of those vectors is 3-dimensional, so actually this is another matrix here. So G1 covers the first row, then G1 the second row, and so on. So then the result is our coefficient matrix, this B times G. So C is what we just saw before, but now we have a connection to geometry. But we need to find out how this connection actually works. Yeah, so B is now our basis matrix, coefficients of our basis functions. So the goal is that we compute them once, and then all that we change is the geometry vector here. So the geometry vector defines the object that we want to have, but the goal is that this matrix is fixed. So we just compute it once and then we leave it fixed. Yeah, and this geometry vector contains boundary conditions, for instance, points, start and end points, or vectors like tangent vectors at the end points. So that's the most generic formulation here. So here we can see it all together. Here on the left we have our helper variable and its exponents as a vector. Then we have our fixed basis matrix, and here we have the geometry vectors. We can also write it back out in full. So here we multiply it back out, and we can see that as the result, this curve, this parametric curve, is the result of polynomials written out here times those geometry vectors. So here we have those 4 vectors, each multiplied with a different polynomial of third order. Right. So this is basically very similar to what we saw in the beginning. We have polynomials times points in space or vectors. Yeah, so we just need to find out how do we need to choose the basis matrix now, right? And what meaning do we want to give those vectors? So that's next. So each curve point is the weighted sum of the elements of the geometry vector, right? And we have a weighting via basis functions. These polynomials, also called blending functions. Yeah, a very simple example is we just have 2 points in space, G1 and G2, which you can see here, G1 and G2. And we want to span a straight line between them, right? So basically our curve starts with u equals 0 here, and then if you increase u, it goes along this line, and for u equals 1, it ends here at G2. And it's actually obvious how to do it. We have 2 polynomials. One is 1 minus u times G1, so that the resulting curve is starting at G1 for u equals 0. And then we have u times G2, such that when u equals 1, then it ends up at G2. And for in-between values, we have the weighted average between the two. Then we can factor this out, and we get 1 times G1 plus u times minus G1 plus G2. Same thing. Yeah, and this can now be used for putting it into our formulation. So here we have our vector of exponents of u. Here's our basis matrix, and here's our geometry vector, which now contains 2 vectors because we just specified 2, right? G1 and G2. And when we look at those numbers here for G1, we get a 1. So that's the 1 here. And for the factor u, we get a minus 1. That's the minus 1 here. So when we multiply this vector, we get minus 1 times u times G1 plus 1 times G1. So these are, well, that's this part or these 2 here. And for G2, we just have the u. So that's why we have the 1 here in this place. That means u times 1 times G2 when you multiply it out. Right. Yeah, so a more useful example is the Hermite curves, or Hermite curves, are named after Charles Hermite. And these are consisting of cubic basis functions, as we just saw. And we have the boundary conditions as endpoints, P1 and P4. But now we also have tangent vectors, gradients in the endpoints. Right. So basically with those tangent vectors, we can specify in which angle the curve ends up in the 2 points. So here we have this geometry vector. Now contains of point 1, point 4, gradient 1, gradient 4. And we need to compute this Hermite base vector, MH. And then the resulting curve would be Q of u equals u times MH times GH. Right, and we still have to find this MH. So here's our geometry vector, and now we can find out the MH, right? The goal now is to find what's actually in the MH. We don't know MH yet. So we know the meaning of the GH, right, our geometry vectors, and that's pretty much all, right? So we need to find this MH. So for that, we make some boundary computations. So here for the starting point, we have u equals 0, right? So we know for u equals 0, q needs to be at P1, right? So q of 0 is P1, right? And that also means that our vector of exponents of u just contains this 1. right? Because here we have u square, u cube, it's all 0 for u equals 0. Right? So this is left of the vector u. Here is the unknown matrix mh, and here is our geometry vector. And we know that the result must be p1 as of our definition, right? We want the curve to start at p1. Same for u equals 1. We just plug it in. Q of 1 must be p4. And this u vector for u equals 1 is all 1s. The rest is the same here. Right? So here we have the second boundary condition. And we have two more for the derivatives, the gradients at the ends. Right? And the derivative with respect to u is basically just taking the derivative of our u vector, right? So here we had 1, derivative of 1 with respect to u is 0, then here this was u, it now becomes 1 as derivative, u square derivative becomes 2u, u cubed derivative becomes 3u square, right? So this is the derivative. Very simple, because here we were able to factor out the exponents of u. Here these are just constant. They stay the same. So now we can do the same for the tangents at the start point and the end point. And we had defined them as R1 and R4. So they are given from the geometry vectors. And we plug u equals 0 in here. So here these terms disappear for u equals 0, so only this is left. And for u equals 1, we just have those coefficients. Right? And now we have 4 conditions, and we can try to find out mh from it. So that's what you can see here. So we took those 4 conditions, put them into this matrix. Right? Here, the mh times the geometry vector stays the same for each condition. That's why we could conveniently put all those coefficients here in one matrix. As you could see here, all those coefficients, here those 4, are put into this matrix here. Right? And on the left-hand side, you had the edge points, P1, P4, and the gradient R1 and R4. Right? And interestingly, when we look at the definition of GH, GH is exactly the same. P1, P4, R1, R4. Right? Same thing. So that means if this is equal this, the right-hand side, then this in the middle must be the identity matrix. Right? So that means here, this matrix with our coefficients times MH must be the identity matrix. And that means MH must be the inverse of this coefficient matrix. Right? This is what we can see here. So here this is the inverse, and if we calculate the inverse, this is what we get. We can, for instance, use Python to compute the inverse of this matrix, and we get this result. And now we have it, right? Now we have our unknown matrix MH. We were successful, and now all we need to do is to choose our geometry vectors to obtain our curve, our parametric curve. Yeah, so that was easy, right? So here this shows the resulting polynomials. So again, we have u, the helper variable between 0 and 1. And here we see u times mh results in those 4 polynomials. Right? For each column of mh, we get another polynomial. Here we can see those 4 polynomials, and here you can see how they look like. So here are the polynomials for R1 and R4. These are the tangent polynomials, and you can see here towards the end they have the gradient 1, and the other has the gradient 0, so that this determines the gradient at the ends. And here we have the polynomials for the points, the endpoints P1 and P4, and you can see here each is 1 at its corresponding end and 0 at the other end. So that makes sense. Yeah. So here's an example. So here you can see the polynomials again. Here you can see P1, P4, and then two end tangents, R1 and R4. And you can see here the curve goes out and goes into the points according to those gradient vectors. So that works. Here are some more examples. 2 points, 2 gradients, and you can see we can control the way the points goes into or out of a point by those gradient vectors. So we get quite different curves depending on how we choose the gradient vectors at the endpoints. Or here this is constant, and here we vary the length of this vector here so that we get different points. Yeah, the problem appears when we have more than 2 points, right? Like here, we have 3 points. And in general, we want to have a continuity in this connecting point. And for that, we need to choose the gradient vectors here such that they point in the same direction. And this actually works best if they both have also the same length. So for G1 and continuity we can have some k, and for C1 continuity this k needs to be 1. Yeah, so that leads us to Bézier curves, because the Hermite curves or Hermite curves they don't really sum up to 1, right? And we found that this is very practical for the convex hull. So this is actually easy to calculate since we have the polynomials now. Here are those 4 polynomials from our Hermite basis functions, and if you calculate it, for instance, using maxima, we see it's again a polynomial, which is unequal 1, right? So the sum is not really equal to 1. So here maxima is actually an open source software which you can use to solve those polynomials, for instance. Yeah, so the reason is that we have 2 basis vectors which are not control points but tangent vectors at the beginning and the end. So that doesn't really fit to a convex hull. So that leads us to the Bézier curves, and they were developed in the 1960s by Pierre Bézier at Renault, and it was a component of the CAD system Unisurf, and it was used in the design of freeform surfaces for automobile production. Concept here is we have a curve contained in a cube, which would be the convex hull, for instance. Start and end points in the opposite corners of the cube. The curve at the starting point is tangential to the x-axis, and the curve at the end point tangential to the z-axis, and the deformation of the curve by deformation of the cube into a parallel epibet. Can be seen here. Right? We have 2 points here, opposite corner of this cube, and you have a smooth curve going from the one to the first to the last. And here you can see that we actually have 4 control points, right? So here P0, P1, P2, and P3. And this curve is determined by those 4 control points. So now instead of having 2 points and 2 tangents, we just have 4 points, right? We replace the 2 tangents by 2 additional points, and 4 points span a cube. Right, so they span a cube, and this cube is then part of our convex hull. Actually, we could make this convex hull smaller by having a plane here. Yeah, so basically we can now come up with Bézier curves with the same way as we did for the Hermite curves by just formulating constraints and then solving them for our basis matrix. Right. So here we also want to have the sum of our basis functions to be 1. So here again is our parametric curve. We have our control points, pi, and these are our polynomials. Here the 3 gives us the order, 3 for cubic polynomials, polynomials of third order. So B are our polynomials of third order. I is naming the control point, and here this I goes from 0 to 3 to cover 4 points. Yeah, and this actually uses Bernstein polynomials as basis functions because they add up to 1, right? For this simple reason. So here you can see the Bernstein polynomials of third order, right here. And in general, you can get those polynomials using this equation here. So you can see lowercase n would be the order of those Bernstein polynomials. Yeah, and we can actually see where they come from by developing the number 1 as a polynomial, right? So it's actually easy enough. So here the 1 can be rewritten as u plus 1 minus u, right? You can see here this u cancels and what's left is the 1. So this is just a fancy way of rewriting the number 1. It's becoming interesting if you square it, right? 1 is also 1 squared, which means you can square this equation here, and then you can factor it out, and you get 3 polynomials, right? And you know they are 1, right? So that means we have now those 3 Bernstein polynomials. Yeah, we can do the same for the power of 3, right? So we write 1 as 1 cube. Here we take this polynomial, take it to the third power, and then we get those polynomials, right? Now we have 4 polynomials, and these are the Bernstein polynomials of third order, and we know they add up to 1, right? So it's actually quite easy to derive them, and for the case of order 3, you can see it's easy to do it by hand. You don't even need a generic formula. Yeah, and they can be used for function approximation, right? Because they have this property that they vary between 0 and 1, and they add up to 1. It's always a weighted sum of some points, and you can use those points, for instance, as neighboring function points, and then just have a smooth curve interpolating those function points, which I show here as an example. So here I have a really simple function, f of u equals 3u. And then we sample this function at 4 points, 0, 1/3, 2/3, and 1, and use Bernstein polynomials of third order for interpolating those sample points, right? And we do it according to this formula here. So we take the sample points, fi over n, right? So these are the sample points. So this actually varies between 0 and 1. So if we have this, for instance, on this interval between 0 and 1, and then these are the points, and here are the corresponding Bernstein polynomials with this helper variable u, which is now going between 0 and 1. Right. So this is what we see here. Down here, here's the interpolated curve. So we have the function value 0 in the beginning, 0 times the first Bernstein polynomial, plus the next function value 1 times the next Bernstein polynomial, then function value 2 times the next Bernstein polynomial, plus function value 3 times the last Bernstein polynomial. And this is then the result, right? We just plug in the polynomials here, and this is the resulting function. And then we can plot it, as you can see here in this plot. So here the blue line is the original function, sampled in the beginning, here twice in the middle, and then in the end. And you can see the red line is our interpolation using the Bernstein polynomials. Right. And you can see it's fitting exactly in the middle and in the end, but not exactly here in the middle. It's approximating the curve quite nicely, but it's not exactly going through those middle points. So imagine these are the points in the cube. Then these middle points would be the points at the edge of the cube. And we saw it's not really reaching those endpoints because they are part of the convex hull. So they are not supposed to touch them anyway. So that's good. Yeah, so this approximation capability of the Bernstein polynomials can also be used in the multidimensional case when we have control points, right? So this leads us to Bézier curves, where we just omit the 3 because we always use third order polynomials. Yeah, and you can also read more here on Wikipedia about the Bernstein polynomial. Yeah, here are some examples. Here we have beginning and end point, and here 2 middle points. And you can see here it's going from exactly the start point and going along the 2 middle points and ending at the end point. Right. And here you can also see the corresponding basis functions. So here are the 4 Bernstein polynomials. And here we just take this point here, the corresponding u. So here is u equals 0, and then here we have some u in between 0 and 1. And here you can see this is the corresponding u here on this plot between 0 and 1. And here you can see the value of the corresponding 4 Bernstein polynomials. Right, and you can see it's the weighted average between all 4 points. And that's also why it's not hitting one of those, because then it would mean that the corresponding polynomial would be 1 and the other ones would be 0. And you can clearly see that none of them is 0. And that's why it goes along. It's only at the endpoints that only one polynomial is 1. So here b3 and here b0 is 1 and the rest is 0. Yeah, so we still need a basis matrix, right? But fortunately we already have the polynomials, so we just can read out the coefficients and put them into a matrix. So this is what I did here. Right, so I'm just taking the Bernstein polynomials of third order, rewrite the polynomial. So here this is 1 minus u to the third power. After a few reformulations you get to this polynomial here. So this is a simple polynomial where we can read out the coefficients immediately. So here we can see coefficient of minus 1 for u cubed, then we have coefficients plus 3 for u squared, then minus 3 for u, and then the 1. Then here b1 was this polynomial factoring out the exponents of u, gives us this polynomial where we can read out the coefficients. So we can plug these coefficients then into our matrix. Remember we had the exponents of u as a vector on the left hand side. So we just need to take these 4 coefficients and put them on the corresponding column of our basis matrix. So here these coefficients would go in the first column, these coefficients go into the second column, these coefficients go in the third column, and this coefficient goes into the last column. So this is what you can see here, right? So here on the left you have the coefficients of u, and here you have the corresponding coefficients. So here is for b0, these are the coefficients for b1, and this is b2, and here b3. Right, here you can see it again. Here are the polynomials, and you can see b0 has minus 1, plus 3, minus 3, and plus 1. So here you can see it, minus 1, plus 3, minus 3, and plus 1, and so on. So we just take those coefficients from the polynomials here and plug them into this basis matrix. And they are then fixed, right? For all Bézier curves, this is a fixed matrix which we store in our software. It's not changed, it's just a constant matrix. So it does not need to be computed every time. Yeah, so that's easy enough, right? So in summary, our interpolated curve is this interpolation between those basis control points. So we have a weighted average. Here are the polynomials, the BIs, and then we put the coefficients of the polynomials here into this basis matrix. Here we have the vector of exponents of u, and on the right we have this matrix of the 4 control points. So here P0 is the first row, this should be P1, and then P2 and P3. Let me see if I can actually change it. Yeah, so this should be P1. Okay. So each control point is a row in this matrix. That's it, right? So here we have a row vector times matrix, and out comes a row vector. Right, and this row vector contains the 3 coordinates of our interpolated point. Okay. Yeah, so the curve now follows the shape of the control points within its convex hull, right? Because we know that the sum of those 4 polynomials is 1. And the movement of a control point influences the shape of the whole curve. It's not locally restricted, right? So if we change one of the 4 control points, that influences the entire curve. The first and last control points form the start and end points of the curve. The basis functions are also affine invariant. And we have a consistency for composite curves, which is not automatically guaranteed. So the same problem if we have 2 curves connecting at some point, then we have to watch that we have this continuity. And we can get it by watching the pair of last control points that they lie on a straight line, right? So here the last 2 control points of the previous curve and the first 2 control points of the next one are basically the same vector up to some constant k, right? So basically they lie on the same line. And we can get it approximately C2 continuous if this k is 1. Right. So I think this should be having an E. Okay. Yeah, so this is what happens if you don't do this. You get a kink here in this curve, right? You don't have a C1 continuity. It's C0 continuous, but not C1 continuous. Here you have those pairs on a line, but with a factor unequal 1. So here we have C1 continuity. Yeah, and here we have a little example in Python. So the following script is a Python example for Bézier interpolation or Bézier curves. We use the same script as in the example for Punkt-interp, where we had some arbitrary polynomials, but now we use Bernstein polynomials, right? So here with this function. So first let's take a look. So copy, and I'm going to my terminal window, which you can see here. So now I'm opening this file. So this is in my directory of my Python examples. So if you do it at home, be sure to be in the right directory. And paste. So here you can see what's inside. So here, as previously, we have our display function. Right here we define our virtual camera, position, the projection. Here we have the orthogonal projection, so not the perspective but orthogonal, the simpler one. Here the viewpoint, here the background colors, the object colors. And here we define points in space. And here we define our control points. So this is P0, P1, P2, and P3. Right. And here we now compute the polynomials for the different values of u. So here you can now see, instead of taking our arbitrary polynomials, we take those Bernstein polynomials. Right. So Bernstein 0, 1, 2, and 3. These are exactly the polynomials that we just saw. Here you can see the values for the different u's, and the u now varies between 0.1 to 0.9 in 10 steps. Right, so for each step you can see the value of the individual polynomials, and you can see the sum of those values. So here the sum needs to add up to 1. Right, and then we can do the interpolation, which you can see here. So we have control point 0 times Bernstein polynomial 0, control point 1 times Bernstein polynomial 1, and so on until we have all 4 points. And this is then displayed, right, with GL vertex. So here, float vector. Yeah, so basically we make those 10 points as interpolation that appear then in our 3D display on our window. So let's run it. Python 3. Yeah, so this is what you get. So let's first take a look here at the output of our prints. So you can see the print outputs. These are the 4 values of our Bernstein polynomials for each u. And here you can see each time the sum. So you can see the sum is 1. That's correct. And here you can see these values are between 0 and 1. So that's also correct. And you can see that's true for each step for u. Those values are always between 0 and 1. And the sum is always 1. For each step, the sum is 1. And the Bernstein polynomial values are also between 0 and 1. So that means we indeed have a weighted average. So that means the points are inside the convex hull. And here you can see it. So the red points are the control points. Right? And the convex hull would be the polygon spanned by those 4 points. And you can see that those interpolated points here, the black ones, are inside this convex hull. So that works. And you can also see they start at the first and end at the last point, and they are just shaped by the in-between control points, but they don't touch them. Right? And it's a straight, smooth curve. Right? So it's nicely round. Right? So that works nicely. Okay. Yeah, so we could also increase, for instance, the number of points to, say, 100. See what happens. Yeah, so then this is what you would get. So this is more a continuous curve in this way when we have 100 points. And you can see here one side is 0.1 and one side is 0.9 for the u. I don't quite know which is which. But it doesn't also really matter. Yeah, so let me go back. So that works nicely. So that confirms that it actually does work. And yeah, this is also kind of a test. So if you have a new, say, a new algorithm, you should always test it, because if it's not working, usually it shows up quite quickly if it's not working, if you test it. Yeah, so here note, the interpolated points are indeed within the convex hull. All factors add up to 1, and the curve begins at the first control point and ends at the last control point. Yeah, so here the objective was a smooth interpolation along all control points. The problem is, for Bézier curves to smoothly interpolate connecting points, the adjacent segments must lie on a line which is a restriction for the control points, right? So that means the designer basically has to take care of connecting all those lines or curves, which is maybe not so good, and that's why there's another approach which is called splines. So this is the next approach, and this is actually the most commonly used approach for computer animation and computer graphics, the splines, which don't have this problem. They automatically nicely interpolate neighboring curve pieces. Yeah, so spline is actually an English expression for an elastic curve ruler, as you can see here. So you can see those ducts here. They are like our control points, and then this elastic ruler is our spline interpolation. So it's basically doing exactly what we want for computer animation. And when you look at this ruler, it aligns itself in such a way that the bending energy becomes minimum, right? Yeah, so actually what's used is the so-called B-splines, B for basis, right? So again, we want to have a basis function as for our Bézier curves and the Hermite curves. And yeah, so the B-splines will actually be the topic of the next video. So thank you for your attention, and then see you in the next video.